Yes, in the previous lecture, we have stopped reading this question. We'll solve this question now. Let's read this again. The wavelength lambda is given. When wavelength is lambda, the stopping potential is found to be x. And when wavelength of light is n lambda, the stopping potential is found to be x by n plus 1. As I said, whenever there is a change in the wavelength of light, the stopping potential will also change, because when wavelength is changed, the kinetic energy, maximum kinetic energy of the electron ejected will also change, and when it changes, stopping potential will also change. So we have to find the threshold wavelength for the metal. What is the threshold wavelength? It is lambda naught. If you remember in my previous lectures, the work function is given by h nu naught. Because if the incident light frequency is nu naught, the threshold frequency, then it will be just sufficient enough to take the electron out of the metal. The kinetic energy will be 0 for that electron. The electron just comes out of the metal surface using this. So that is equals to the work function, minimum energy required to take the electron out. So phi equals to, I can write it as hc by lambda naught, right? We are supposed to find this threshold wavelength for this problem, for this question. Now let's see. Now first, what is the first case? We know, let's write the equation, general equation. What is that? EV naught is h nu minus phi. EV naught is h nu minus phi. Now what is V naught? In the first case, when wavelength is lambda, let's write this. Instead of nu, I'll write it as hc by lambda, or I'll write it in the next step. So E V naught equals to hc by lambda minus hc by lambda naught. This is phi, hc by lambda naught. Now in the first case, what is V naught? V naught is x. So I'll write it as x, Ex equals to hc by, what is wavelength? The wavelength of light is just lambda. So hc by lambda, no change, minus hc by lambda naught. This is for the first light. Now for the second light, what is the wavelength? N lambda. And stopping potential is x by n plus 1. So second equation I can write as Ex by n plus 1 equals to hc by, wavelength is n lambda minus hc by lambda naught. Now according to the given data, you have these two equations. The procedure is just we have to solve these two equations in order to find lambda naught. We have two equations, and the unknown lambda naught can be found out by solving these two equations. So let's say this is equation 1, this is equation 2. Now the solving of equations, there could be many methods to solve. So what I do is, I'll take this n plus 1 to the right hand side, then Ex, left hand side only Ex will remain here in this equation, and Ex is there in this equation. I can equate these two, which means that I can equate these two. So in other words, the second equation can be rewritten as Ex equals to n plus 1 into this whole term, hc by lambda n lambda minus hc by lambda naught. This is your second equation. I've rewritten the second equation. Now since these two are equal, I can equate these two and solve it, find the lambda. This is the simplest procedure that I follow. Or else you can choose some other methods. You can take lambda naught from here, put it here. According to your convenience, you can proceed. Let's go by this now. So you have two equations now. So what I do is, so from these two equations, I can write it as, I'll write down here. From equation 1 and 2, from 1 and 2, this, instead of Ex, I'll write this entire term, m plus 1, or I'll write it here. This equals to this entire term, m plus 1 times hc by lambda n lambda minus hc by lambda naught. Now solve this equation. So hc by lambda minus hc by lambda naught, no change on the left hand side. Let's expand this. It becomes nhc by n lambda plus hc by n lambda minus nhc by lambda naught minus hc by lambda naught. I've just multiplied this n with this term and 1 with this term, you will get this. Now nhc by n lambda, I can cancel these two n's, right? So cancel up these two n's, n cancel. Any other cancellations? hc by n lambda, hc by. Now if you see this hc by lambda here and minus hc by lambda naught, you have the same hc by lambda minus hc by lambda naught. So I can cancel this and this, minus hc by lambda naught minus hc by lambda naught. Then only these two remain. These two terms are there, so I can write it as only these two are there. So on the left hand side you have nothing, 0 equals to hc by n lambda minus nhc by lambda naught. Now it is easy. Take this on the other side, then find lambda naught from this. So what it becomes, if you take this to the other side, you will become you will get hc by n lambda equals to nhc by lambda naught, right? I can write this, hc by n lambda is nhc by lambda naught. Therefore lambda naught is how much? Lambda naught, take lambda naught on the other side, on one side. So lambda naught equals to nhc divided by hc into n lambda, right? So hc I can cancel up, hc. Therefore the remaining terms are n into n lambda. Therefore lambda naught is n square lambda. So this is the threshold wavelength. It is equals to n square lambda. When you have two different stopping potentials for two different wavelengths of light, right? Yes. So this is the relation. That's it. Lambda naught is n square lambda. Let's move on to the next one. Find the threshold wavelength. Find the threshold wavelength of light that would produce photoelectrons for a silver surface the work function for silver is .8 electron volts. This is also easy. I have to find the threshold wavelength. The work function is given. Threshold wavelength you have to find. So in order to find the threshold wavelength, you have the equation. Simple equation is phi equals to h nu naught. That's it. The work function is h nu naught or hc by lambda naught. since wavelength is given, hc by lambda naught. So we have five values given, so we can find the threshold wavelength from this. It's easy. Lambda naught is h is 6.63 into 10 power minus 34 into 3 into 10 power 8 divided by 5. What is 5? 4.8 electron volts. So 4.8 into 1.6 into 10 power minus 19. Converting into joules. Now simplify it, we'll get it. 3 ones, 3, 1.6. So 1.6 into 1.6. Okay. Let's take these terms. Let's see these terms. So this is 19 plus 8. So that is 27 minus 34. So 10 power minus 7 will be 10 power minus 7. This is 6.63 divided by 1.6 into 1.6 is 2.56. 2.56, 6.63 by 2.56, you will get roughly around 2.5. So I can take it as, it is roughly, I'm doing some approximation, roughly it will be from 2.59 like this, 2.59, 2.5, 2.6 let's say, or say 2.6, 2.6 into 10 power minus 7, I can write it as 260 nanometers, 260 nanometers. We are doing some approximations, we are not worried about the exact value, since it takes a lot of time, let's do some approximation, 2.5 or 2.6, 260 nanometers. Whichever is close, you can mark that answer in the examination. So that's it, it's very simple. Next one. So I'll give one practice sum for you. So Q, calculate the possible velocity of a photoelectron if the work function of the target material is 1.25 electron volts and wavelength of light is 4.36 into 10 power minus 7 meters. What retarding potential is necessary to stop the emission of electrons? So this is a practice sum for you. We have done these kind of sums in the previous case. So what is given? Work function is given and wavelength of light is given. So work function we know, wavelength of light we know. We have to find the retarding potential and the velocity of photoelectron. So just use this equation, EV naught is h nu minus phi. Phi is there, nu c by hc by lambda, lambda is known. So you can find V naught from this equation. And then once you get V naught, you can find the velocity. What is velocity? EV naught is the Ke max. So this is EV naught is Ke max. Once you get V naught, and that Ke max is half mv square. We have done this kind of problems. So equate this, you know the mass of the electron Find V from this equation. Simple. So you can do this. Next one. I will give one more practice sum for you. Two identical photocathodes because this is also easy. Two identical photocathodes receive light of frequencies F1 and F2. If the velocities of photoelectrons of mass m are V1 and V2 respectively, then prove that, then show that V1 square minus V2 square equals to 2h by m F1 minus F2. So two frequencies are given and the electrons are moving with the different velocities. Use the photoelectric equation, solve the two equations for the two different frequencies. If you solve that, you will get this, you will arrive at this equation. This is also very simple. Yes? Let's go. So, enough of questions on photoelectric effect. Now let's move on to the questions based on the de Broglie's wavelength. I will solve some few questions finding the de Broglie wavelength or momentum kind of problems, matter waves. So first one, calculate the de Broglie wavelength of 0.2 kg ball moving with a speed of 15 meters per second. 15 meters per second. So you have a ball whose mass is 0.2 kg moving with the speed of 50 meters per second. So you have momentum for that ball. So what is the wavelength formula? I have given lambda is h by p, h by mv. So simply is 6.63 into 10 power minus 34 divided by what is mass? It's 0.2 into 15. So 6.63 into 10 power minus 34, 0.2 into 15 is 3. So therefore the answer will be roughly 2.21 into 10 power minus 34 meters. Have you seen the wavelength here associated with the ball whose mass is 0.2 kg and moving with the speed of 15 meters per second? It is 10 power minus 34. It is order of minus 34 meters. That's why I said in my previous lecture, you cannot see the waves associated with the macroscopic bodies because of their huge mass compared to the masses of the subatomic particles. If you have an electron and proton, the wavelength will be appreciable. It will be in few nanometers or angstrom range. But here it is more than that, 10 power minus 34 meters, which is we cannot differentiate, you cannot find, you cannot observe the wave-like nature associated with these macroscopic bodies. That is because of the huge masses. So this wavelength is always appreciable only for subatomic particles whose masses are very lesser. If you take the electron mass, the mass of the electron will be 10 power minus 31. 9 into 10 power minus 31 kg, right? Then if you take the 31 out, 31 minus 3, 10 power minus 3 range, in that range you will get. So which is, the wavelength is more compared to this. This is negligible. That's why we don't see a wave-like nature associated for the macroscopic bodies. This wave-like nature is still there, but we cannot see it. That's why classically we don't take this wave-like nature. But even though waves are associated, this wave nature is associated for all the particles, whether it is microscopic or macroscopic, we don't observe it. It is not that appreciable level. So the wavelength is 2.21 into 10 power minus 34 meters. Let's move on to the next one. A proton and an electron have same de Broglie wavelength. Which one has greater kinetic energy? This is just like a reasoning question. Two particles are there, proton and electron. Both have same de Broglie wavelength. What is de Broglie wavelength? Lambda is h by p. It is h by m into v. Now for the two particles, for proton and electron, the wavelength is same. Meaning what? Lambda for proton p equals to lambda for electron e, which means h by mp vp equals to h by me ve, where the subscript p represents for proton and e represents electron. So we have this equation. If they have, we know that the mass of electron is lesser than the mass of proton. So obviously we can say the velocity for the electron will be more. Since h is common here, so I can write it as MEVE equals to MPVP. So directly by reading the question itself, we can say the mass for electron is lesser compared to the mass of proton. Then what happens? The velocity of the electron should be more compared to the velocity of proton. Since these two are same, the momentum for these two particles are same, momenta are same. So therefore, when velocity is greater for electron, the kinetic energy also is greater for electron, right? Yes. So therefore, the kinetic energy will be maximum for electron. Moving on to the next. Find the ratio of de Broglie wavelength of molecules of hydrogen and helium which are at temperature 27 and 127 respectively. Now two molecules are there, hydrogen molecule and the helium molecule, which are at different temperatures. We have to find the de Broglie wavelength associated for that. Now before that, let me tell you, we know this lambda is h by p, that is h by mv. Now the mass as well as the velocity, both are not given here. Then how to proceed, how to find the wavelength here? It is given only the two molecules are at different temperatures. Hydrogen is at 27 degrees centigrade and helium is at 127 degrees centigrade. Now this is something confusing. But when a molecule, when it is given some particle is at a different temperature, is at a particular temperature, let's say, what is the energy possessed by that particle? If you go back to the kinetic theory of gases, the energy possessed by the particle at a given temperature T is E is 3 by 2 kT. If you recollect this, the translational energy possessed by the particle at a temperature, given temperature T is 3 by 2 kT. If you recollect the concepts of kinetic theory of gases, where K represents the Boltzmann constant. K represents the Boltzmann constant, T is the temperature in Kelvin. So this is the energy possessed by these molecules. Now we have momentum here. Can we connect this energy and momentum? Can we connect this? We have kinetic energy of a particle is p square by 2m. There is a relation between energy and momentum. So what is p then? P equals to 2m ke, or simply represented is E. This kinetic energy is E, 2me. So now what I do is I'll just substitute E value there, then I'll get P is 2m into 3 by 2 kT under root. This is equals to 3m kg. So this is the value of P when two molecules are given at different temperatures. Now what we do, for the first molecule you use this, instead of P you put 3m kT at first temperature, then for the second molecule put T as 127, not 127, these are in degrees centigrade, we have to convert that in Kelvin, this temperature is in Kelvin, so add 273 and 273 here, we put that value and then find the ratio of the wavelengths. We'll do this, we'll see the answer, how to proceed in the next lecture. So this is the momentum in terms of temperature. So now what I do is, I'll write this. So lambda is h by 3m kT. Now take the hydrogen molecule first. So lambda hydrogen H2 equals to h by 3m k. Temperature is 27 degrees centigrade. 27 is 27 plus 273, which is 300. This is the mass of hydrogen. K is the Boltzmann constant. Now for helium, it is h by 3 mass of helium, Boltzmann constant, into 273 plus 127, you get 400. Now take the ratio of these two values. Ratio of first one is hydrogen, right? So lambda H2 divided by lambda He. So this divided by this, it will become 3m, or all these common terms get cancelled up. You'll be having only mass of helium into 400 divided by mass of hydrogen into 300 under root. As we see, the common terms will get cancelled up. H, K, 3, all these terms cancel up. What is this value? What is the ratio of mass of helium and mass of hydrogen molecule? We are taking hydrogen molecule H2. If this is M, let's say each hydrogen is having mass of each hydrogen is M, then for hydrogen molecule it is 2M because 2 protons are there in this. What about helium? In a helium, 2 protons and 2 neutrons are there. Then the mass will be equal to 4M. Here 4 nucleons are there, here 2 nucleons are there. So the ratio will be 4M by 2M. So I can write it as 4M into 400 divided by 2M into 300. Now this is equals to 8 by 3, root 8 by 3. This is the ratio. This is the ratio of the wavelengths for hydrogen molecule and the wavelength for helium molecule. This is how we proceed. We just have to remember what is the mass for the hydrogen as well as what is the mass for the helium. Then temperature has always to be converted in Kelvin, not in degrees centigrade. Then this is the values written with. We'll continue this in the next lecture.